Hello, my name is Kevin Craig. This presentation is an introduction to mechatronics, innovation, and the physical and mathematical modeling of mechatronic systems. Modeling is the cornerstone of modern engineering practice. Hello, my name is Kevin Craig. How does a company get a competitive advantage in the 21st century? Innovation happens when a human need or problem is identified and thoroughly understood, and technologically feasible solutions are created that are viable and sustainable from a business point of view and usable from a complexity point of view. Innovation is local. You don't import it, you don't export it, you create it. It is a way of thinking, communicating, and doing. How are engineers transformed to change the world in the 21st century? The 21st century engineer is a T-squared engineer, an engineer who has depth in an engineering discipline, but also multidisciplinary engineering breadth. And in addition to the technology depth, that engineer will have non-technical breadth in business, human values, social science, and managing complexity. How are engineers transformed to change the world in the 21st century? The 21st century engineer is a T-squared engineer, an engineer who has depth in an engineering discipline, but also multidisciplinary engineering breadth. And in addition to the technology depth, that engineer will have non-technical breadth in business, human values, social science, and managing complexity. All systems today are multidisciplinary. The modern multidisciplinary engineering system consists of a physical system, the plant or process which is the subject of our attention. Actuators make things happen. Sensors tell us what's happening. The complex decision-making the engineer creates is executed in real time by a computer. It is most important that in system design, the system dynamics and the control structure be considered simultaneously. Innovation, integration, optimization are all done simultaneously from the beginning of the design process. Performance, reliability, low cost, robustness, efficiency, and sustainability are absolutely essential. If all systems look like this, who will design them? All multidisciplinary engineering systems are created by a multidisciplinary design team, whose essential members are a mechanical engineer, a computer systems engineer, a controls engineer, and an electrical electronics engineer, all working together with no silos and no comfort zones. If this is the way systems are created, who will lead this team? The diagram you see, I created in 1995 as a professor at Rensselaer Polytechnic Institute. It is now used throughout the world to represent the multidisciplinary field known as mechatronics. Mechatronics is the synergistic integration of physical systems, electronics, controls, and computers through the design process from the very start of the design process, thus enabling complex decision-making. Integration is the key element in mechatronic design, as complexity has been transferred from the mechanical domain to the electronic and computer software domains. Mechatronics is an evolutionary design development that demands horizontal integration among the various engineering disciplines, as well as vertical integration between design and manufacturing. Mechatronics is the best practice for synthesis by engineers driven by the needs of industry and human beings. It is technology integration to achieve optimal system functionality. Balance. Balance is the key to success, both in life and in multidisciplinary system design. A balance between theory, that is modeling and analysis, and practice, experimental validation, and hardware implementation. Computer simulation without experimental verification is at best questionable and at worst useless. Present-day engineering education requires a new engineering mindset. Multidisciplinary systems, like the environment, are complex, and in a complex system, learning how all the pieces, constant and variable, interact gives a depth of understanding that averts catastrophe. Human-centered design, that is, understanding the interfaces among technology, people, communities, governments, and nature, is what makes complexity manageable. Clearly, the typical discipline-specific engineer is not well equipped to manage such complexity. Not even an engineer with multidisciplinary engineering breadth can do an effective job. Complexity demands a skill set illustrated by the T-squared engineer, one with technology depth and also non-technical breadth, specifically human-centered design expertise capable of managing complexity. As most of the challenges society faces are multidisciplinary, teams of T-squared engineers will be at the core of the multidisciplinary human-centered design team. Each of these T-squared engineers will have depth in mechanical, electrical, or computer systems engineering, and all will have knowledge in the design and implementation of computer control systems. Communication is key, both among these individuals and with other experts, and modeling facilitates insight and communication. Modeling is the universal language for innovation. As the diagram shows, comfort zones and silos must be avoided, as they are the greatest impediments to effective communication and innovation. Over the past 30 years, the cost of technology has plummeted. However, the available information and the complexity of the systems we design and build has grown exponentially. Human evolution has remained effectively constant. What will bridge this gap between human evolution and the amount of information available and the complexity of the systems that are being designed and built? The answer is human-centered design. Human-centered design requires interdisciplinary collaboration, an iterative process with frequent prototyping, and engagement with real people. Once a system is in development, correcting a problem costs 10 times as much as fixing the same problem in design at the concept stage. If the system has been released, it costs 100 times as much. Challenges are met and problems are solved by changing culture, attitude and behavior, and instilling ownership. Nothing short of this will do. In the history of the world, no one has ever washed a rented car. I often hear engineers say, I have taken all the engineering courses and labs. I have an engineering Bachelor of Science degree. I have many years of experience as a practicing engineer. Why then, when I am faced with a multidisciplinary engineering problem, which they all seem to be now, sensors, actuators, real-time computer control, electronics, mechanics, why do I feel like this, what this cartoon shows? Well, what engineers need and what they will rely on is a process that takes them from the identification of the need through the problem solution. And a key element in that process is modeling. Modeling is the cornerstone of modern engineering practice. And in modeling, the first step is the key. Often engineers will have a physical system that they wish to understand or improve, or they have a design concept to solve a problem, to meet a need that was presented to them. The first step in this mechatronics system design process is to create a physical model through the use of engineering judgment and simplifying assumptions. The process that will guide engineers in the solution of multidisciplinary problems is the mechatronics system design process shown here. We will be applying this process throughout this course. Basically, the process consists of control-oriented physical modeling, mathematical modeling using laws of nature, dynamic response prediction by simulation, experimental validation of prediction, control system design, and we evaluate both system design and control system together to meet dynamic, not static, dynamic performance requirements. There are three approaches to that important first step, physical modeling: white box modeling, gray box modeling, black box modeling. In white box modeling, we rely entirely on first principles. In black box modeling, we base the physical model entirely on experimental input-output measurements. And then quite naturally, practicing engineers use a combination of both white box and black box models to create what we call a gray box model, a model based on first principles and experimental measurements. Take a break from the presentation. Shown here is a picture of an automobile shock absorber. How would you model an automobile shock absorber? Think about it in terms of white box, black box, and gray box modeling. Here is an example. Consider an automobile shock absorber. Looking from the inside, it consists of a cylinder surrounding a movable piston. Moved by a shock from the outside, the piston compresses oil inside the cylinder through holes in the wall, thus dampening oscillations. A spring pushes the piston back to its original position, and a rubber stopper prevents the piston from impacting the walls of the cylinder when shocks are too strong. The shock absorber comprises the interaction of the mechanical movements of rigid bodies, the viscoelastic dynamics of fluids, the elastic behavior of springs, and the deformations of elastic plastic materials. Looking from the outside, we only are aware of the phenomenological properties. We observe aspects like nonlinear stiffness, nonlinear viscous damping at high frequencies, and hysteretic effects at low frequencies. But we are not able to assign these phenomena to the individual parts of the shock absorber. Looking from the inside, we apply the laws of nature, together with the constitutive equations of the components, to the physical model to generate the mathematical equations of motion. These are solved by numerical simulation to predict the behavior of the physical model, which must be experimentally verified. Because we use our insight and understanding of the way the system works to create the model, we call this model a white box model, and it is an approximate image of the physical system. Looking from the outside, measurements alone of the real system give no insight into the real system, and thus no understanding of how the real system works is brought into the construction of the model. A mathematical model is chosen which fits optimally the measured data. This type of model is called a black box model. White box models are approximations of reality and always need experiments to identify parameters in the model, validate model predictions, and show where the model is deficient. The set of possible black box models should always be guided by some knowledge of the inner workings of the real system. Since the focus of the engineer is solving the problem, the gray box modeling approach is intuitive and obvious. Consider the Electro-Pneumatic Transducer. It's an off-the-shelf item, but to the engineer designing this system, it is a true multidisciplinary engineering system. Here's a picture of this off-the-shelf component. Here is a sketch showing its key components. Here's a block diagram describing its operation. The device is meant to convert an input voltage in the range of 3 to 15 volts to an output pressure in the range of 3 to 15 psig. It does that by first sending a voltage to a coil of wire in a permanent magnetic field. Here's the voltage. The voltage gets applied to a coil. In the coil, a current flows and creates a magnetic field. That magnetic field interacts with the permanent magnetic field shown here. Another way to look at it is that the current carrying coil feels a force in this external magnetic field called the Lorentz force. So there's a magnetic force acting on a spring mass damper system. Where are the springs? These cantilever beams are springs. The mass is the rod with a damper float device at the bottom. The cantilever beams are both springs and dampers, as they are most likely coated with some elastomer material to give them some element of damping in addition to stiffness. The float in this viscous fluid acts like a viscous damper, and the mass, of course, is the mass of the rod. We have a spring mass damper system. As a result of the force, we have a change in position designated by x sub f. X sub f changes the distance between the flapper and this nozzle, which affects the output pressure of our system. So there's a pneumatic subsystem that describes the relationship between the flapper motion and the output pressure. However, there are some natural feedback elements in this system. One is that there's an added force to the spring mass damper system because the pressure here, output pressure, exerts a force over the area of the flapper. So pressure times area gives us a pressure force, which gets subtracted from the magnetic force. In addition, whenever we have motion of a coil in a magnetic field, we induce a voltage by Faraday's law. And that voltage that gets induced is proportional to the velocity of the coil. So x sub f is the motion of the spring mass damper system to which the coil is attached. If I take the derivative, I get velocity. Velocity times a constant, the coil circuit voltage generator effect constant, or the back EMF constant, gives me a voltage that gets subtracted from the input voltage. So what we have here is an off-the-shelf item that is a true multidisciplinary engineering system. If I now make simplifying assumptions and use engineering judgment and apply those assumptions to my physical model, and I identify the relevant parameters, I come up with a mathematical model by applying the laws of nature to my physical model. You see here in this block diagram, the words describing the operation of the subsystems have now been replaced by transfer functions, algebraic expressions describing the operation of those various subsystems. The design engineer needs to understand all of these subsystems and how each of the subsystems operate in order to properly design the system for some performance. And also, if the system needs to be improved or changed, this type of mathematical description is absolutely essential to understanding the system and how it can be improved. Another example of a multidisciplinary engineering system is the electrodynamic vibration exciter. We see a physical system picture here of a very large exciter, and in the lower right corner, a much smaller handheld vibration exciter from Brüel & Kjær. Both operate on the same physical principles. However, the smaller exciter has a permanent magnet, while the larger system has an electromagnet. Key attributes of this system include inertia, compliance, friction, resistance, inductance, magnetic flux, reluctance. Variables used to describe this system include position, velocity, voltage, current, magnetic flux. Here we show a physical model of this physical system based on simplifying assumptions and engineering judgment. And I represent these attributes by using what we call pure and ideal elements. While pure and ideal elements do not actually exist, because a pure element is an element that only has the attribute for which it is named, and most elements have parasitic effects. Ideal means linear, and all physical devices and systems are nonlinear in nature and only operate in a linear fashion over some range of operation. Nevertheless, they are useful in representing the key attributes, and in combination can represent real, actual devices, real, actual behavior. Here is a picture of the Mars Exploration Rover #1. An electrodynamic vibration exciter was used for the vertical axis landing loads pulse testing. And the exciter used was a B&K electrodynamic vibration shaker. A water-cooled electrodynamic shaker for shock and high-performance vibration tests of extra-large payloads up to 5,000 kilograms, such as satellites, electronic assemblies, and defense hardware. This exciter has a peak sine force rating of 289.1 kilonewtons. The electrodynamic vibration exciter is a moving coil type of device that converts an electrical command signal into a mechanical force and/or motion, and is very common. For example, vibration shakers, loudspeakers, linear motors for positioning heads on computer disk memories, and optical mirror scanners. In all these cases, a current-carrying coil is located in a steady magnetic field provided by permanent magnets in small devices, and electrically excited wound coils in large ones. Two electromechanical effects are observed in such configurations. The generator effect, where the motion of the coil through the magnetic field causes a voltage proportional to velocity to be induced into the coil. And the motor effect, the passage of current through the coil causes it to experience a magnetic force proportional to the current. We use pure and ideal elements to represent the attributes, the physical attributes of this system. There are cantilever beams that act as a spring damper system. The flexure K sub F is an intentional soft spring. It's a pure and ideal element, but it's meant to represent the compliance of that cantilever beam. It's very stiff in the radial direction, but very soft in the vertical direction, as the exciter is meant to move just vertically up and down. And this cantilever beam spring serves to guide the axial motion of the coil and table. The elastomer coating on the cantilever beam gives the beam damping. This flexure damping B sub F is usually intentional and fairly strong, and it's obtained by a laminated construction of the flexure spring using layers of metal, elastomer, plastic, and so on. However, there's a non-ideal aspect to this system. The coupling of the coil to the shaker table would ideally be rigid, so that magnetic force is transmitted undistorted to the mechanical load. However, this is not the case, and we see this demonstrated at high frequencies. So this is a parasitic effect, and we model this parasitic effect with a KT, a spring constant that's generally large, and a B sub T, a viscous damping coefficient that's quite small, and this represents parasitic effects. And these are not intentional spring damper elements, are not designed in, but are just used to represent the fact that the coupling of the coil to the shaker table is not rigid. It's not ideal. The resistance and inductance, R and L, are the total circuit resistance and inductance, and these again are pure and ideal elements, again representing the distributed attributes of resistance and inductance in the electrical subsystem. And these include contributions from both the shaker coil and the amplifier output circuit. Here we see actual frequency response plots for typical values of an electrodynamic vibration exciter. And we see that in this spring mass damper system, we have a resonance. It's a very highly damped resonance, and that's completely expected. However, due to the non-rigid coupling of the coil to the table, we have a very lightly damped high-frequency resonance. It's a parasitic resonance due to coil-table coupling. However, we do not need to be concerned about this if we're operating in a low frequency range with this device. So while we have a model that captures performance over a very wide frequency range, if our range of operation is limited to a lower frequency range, this parasitic effect need not be of concern. Take a break from the presentation. The picture on the left shows an engine dynamometer, and the sketch on the right shows the features of that dynamometer. If we want to understand how the dynamometer works, we need to create a physical model and then a mathematical model. What simplifying assumptions would you make to create the physical model of this engine dynamometer? Shown is another example of that first step, going from the physical system to the physical model. We see an internal combustion engine connected by a transmission shaft to an eddy current dynamometer mounted in trunnion bearings. And below you see the physical model of this physical system. Let's understand the elements of the physical model and how it was developed. So I've reproduced the physical system and physical model pictures on this slide. The figure above shows an internal combustion engine connected to an eddy current dynamometer, very common physical measuring device. The physical model is also shown. The engine is considered a nonlinear angular velocity source, omega sub e. Omega is angular velocity in radians per second. And we modulate that by a throttle setting, theta, a function of time. The main energy storage is associated with the rotating inertia, J sub E, of the engine. That's energy stored in the kinetic energy of that rotating inertia. And we lump that at the output of the engine shaft. The torque transmission shaft has compliance, it's not a rigid shaft, and also energy dissipation. And we model that by using a pure and ideal rotational spring, K sub S, and a pure and ideal rotational damper, B sub S. So these are pure and ideal elements meant to capture the attributes of compliance and energy dissipation of this torque transmission shaft. We neglect the inertia of the shaft. However, we could include that shaft inertia either with the engine inertia or with the rotor inertia of the dynamometer, should we think that desirable to do. It certainly can be done at a later stage. The dynamometer consists of a toothed rotor, J sub r, which rotates with an angular velocity omega sub r. And this rotates in the magnetic field created by passing current, I sub F, a function of time, through the stator windings. A voltage is induced in the conductive rotor rotating in the stator magnetic field according to Faraday's law. This induced voltage creates eddy currents in the rotor, which generate a magnetic field, according to Ampere's law. And this magnetic field opposes the stator magnetic field, according to Lenz's law. The stator inertia, J sub S, is mounted in trunnion bearings and is free to rotate, but we restrain it by a torque arm to measure the torque developed. The spring K and damper B are also pure and ideal elements, and they represent the compliance and energy dissipation associated with the torque measurement. So we see that the key elements in creating physical models is being able to assign pure and ideal elements to represent the real attributes of the physical system, and to understand multidisciplinary physics and the laws of nature to understand the behavior of this multidisciplinary device. Question is often asked, can physical system modeling be taught? Is it an art or a science? Many engineers have little experience and hence little confidence in doing it. Well, that's only natural because in engineering schools, it is not taught. Usually a problem starts with a physical model having already been created. The first step is not described. The first step, going from the physical system to the physical model, is not practiced. Most engineering teachers also have no experience in actually performing that first step. Physical system modeling either applied to an existing system or a concept in the design process, leads to thorough understanding. It differentiates engineers and gives companies a competitive advantage as it leads to innovation. Successful physical system modeling requires a fundamental understanding of multidisciplinary physics and a commitment to do it, not fall back on the old design, build, test approach. This is the most direct path to innovation. In design, an engineer rarely starts with a blank sheet of paper. Designs are usually the result of the improvement of an existing system, the innovative combination of existing systems, or the application of new technology or new knowledge to an existing system. In all this, understanding what exists is paramount, and modeling is essential to that understanding. The purpose of modeling is insight. Also, once a concept has been developed in the conceptual phase of design, it is evaluated through modeling, not by building and testing. The physical system, sensors, actuators, and controls all integrated into the design concept. No afterthought add-ons are allowed. Ask 6 engineers what a model is, and you may get 6 different answers. The word model has a specific meaning, and modeling is the single most important activity in the modern multidisciplinary engineering system design process. There are actually 2 distinct models of an actual dynamic physical system, a physical model and a mathematical model, and the distinction between them is most important. In general, a physical model is an imaginary physical system, a slice of reality. And in modeling dynamic physical systems, we use engineering judgment and simplifying assumptions to develop a physical model. The challenges to physical modeling are formidable, as the dynamic behavior of many physical processes is very complex. As shown, there is a hierarchy of physical models of varying complexity possible, from the less real, less complex, more easily solved design model to the more real, more complex, less easily solved truth model, with a control-oriented model in between. The complexity of the physical model depends on the particular need. For example, system design iteration, control system design, control design verification, physical understanding. Always ask the question, why am I modeling? An excellent analogy is geographic maps and the varying detail one can display on a map. The intelligent use of simple physical models requires that we have some understanding of what we are missing when we choose the simpler model over the more complex model. The astuteness with which simplifying assumptions are made at the onset of an investigation is the very crux of engineering analysis. The ability to make shrewd and viable approximations, which greatly simplify the system and still lead to a rapid, reasonably accurate prediction of its behavior, is the hallmark of every successful engineer. Once a physical model has been developed, the appropriate laws of nature, Newton's laws, Maxwell's equations, conservation of mass and energy, are applied to the physical model to generate the mathematical model, the differential equations describing the dynamic behavior of the physical model. Photographs do give us nice bright colors and the greens of summer, and they do make you think all the world's a sunny day. But we don't need Kodachrome film anymore, as the digital image sensor, the heart of all digital cameras, has replaced film. It is the component that converts the light coming from the subject being photographed into an electronic signal. If you have a roll of Kodachrome film, you could not get it developed anywhere in the world. On December 30th, 2010, at Dwayne's photo in Parsons, Kansas, the last rolls of Kodachrome film in the entire world, with all those nice bright colors, were processed. This is hard to believe, yet it is true, and it dramatically shows how digital the world has become. But how many people, engineers included, really understand the difference between the analog and digital worlds and the key issues involved in going from one to the other. For some, it is just a curiosity, but for all engineers, it is an absolute necessity. Why do wagon wheels in a movie sometimes appear to rotate backward, while the wagon is actually moving forward? When you hear music in the background while on a cell phone, why does the music sound flat or distorted? The answers to questions like these are found in understanding the fundamental concepts of digitization, sampling, aliasing, and quantization. Digitization, or analog to digital conversion, is the act of converting an analog signal, which is continuous in both time and amplitude, to a digital signal, discrete in both time and amplitude. Discrete values in time are the result of sampling an analog signal, and discrete values in amplitude are the result of representing those values using a finite number of bits. That's quantization. There are a few fundamental concepts that every engineer needs to understand very well. Fourier showed that any waveform that exists in the real world can be generated by adding up sine waves of different amplitudes, frequencies, and phases. And that representation is unique. And Nyquist showed that a sampled signal can be converted back to its original analog signal without any error if the sampling rate is more than twice as large as the highest frequency of the signal. The digital to analog converter accomplishes that task. If this Nyquist sampling theorem is violated, an inevitable, irreversible effect called aliasing results. Aliasing cannot be eliminated completely, only reduced with an anti-aliasing analog filter before sampling takes place. The effect of aliasing is that frequencies above the Nyquist frequency, which is 1/2 the sampling frequency, are folded back into the useful frequency range and appear indistinguishable from the real signals. For example, a tone 1 kilohertz above the Nyquist frequency will fold back to 1 kilohertz below, while a tone 1 kilohertz below the sampling frequency will appear at 1 kilohertz. The control system will respond to both signals, real and fictitious. The anti-aliasing filter will limit performance because of time delay, but the effects of aliasing are much worse. The accuracy achieved in a digital memory device depends on the number of bits used for storage of each sample. Quantization is the process of changing the sample values to discrete levels and results in errors called quantization noise, because the effect sounds like noise in a digitized music signal and looks like noise in a digital image. The measure of the relative size of quantization noise is called the signal-to-noise ratio, and it is given by a simple formula, 2 raised to the power b, where b is the number of bits used to store samples. Shown are the signals in a computer-controlled system. A signal that is continuous in amplitude and continuous in time is an analog signal. We see it here in the table, continuous in amplitude, continuous in time. A signal that is discrete in amplitude, that is quantized, and discrete in time, that is sampled, is a digital signal. We see that here in the table, discrete in amplitude, discrete in time. In between these two extremes, we have two other signals. A signal that is continuous in amplitude, but discrete in time, we call a sampled signal. So this is a signal that is continuous in amplitude and discrete in time, a sampled signal. A signal that is discrete in amplitude but continuous in time is called a quantized signal. So it's discrete in amplitude and continuous in time. These are the four categories of signals that appear in computer-controlled systems. Shown is a typical computer control configuration. This is a feedback control system. G of S is the plant, the output of which we wish to control. H of S is the feedback element. The output of G of S and of H of S are analog signals, continuous in amplitude, continuous in time. That signal is compared to our command in the summing junction. The output of the summing junction is an analog signal, continuous in amplitude, continuous in time. It is then sampled, which makes it a sampled signal, continuous in amplitude, discrete in time. It is then converted to an analog signal, making it continuous in time through what we call a zero-order hold element. This analog signal, continuous in amplitude, continuous in time, is then converted to a digital variable, discrete in amplitude, discrete in time, through the analog to digital converter. This is where your digital compensation takes place. All the calculations here are digital. The output then of the digital compensation, which is a digital variable, needs to be made continuous in time to be sent to a continuous system, G of S. So the D to A converter converts this digital variable to one that is still discrete in amplitude because it's represented by discrete levels, bits, but now is continuous in time. A continuous in time signal needs to be sent to this continuous system in order to cause it to respond. So you see how these four categories of signals appear in a feedback computer control system. Analogies give engineers insight. Insight based on fundamentals is the key to innovative multidisciplinary problem solving. A person trying to explain a difficult concept will often say, well, the analogy is. The use of analogies in everyday life aids in understanding and makes everyone better communicators. Mechatronic systems depend on the interactions among mechanical, electrical, magnetic, fluid, thermal, and chemical elements, and most likely combinations of these. They are truly multidisciplinary, and the designers of mechatronic systems are from diverse backgrounds. Knowledge of physical system analogies can give design teams a significant competitive advantage. To explore in some depth the nature of physical system analogies, let's use the common electrical mechanical analogy. Here is the model structure for electrical systems. The key attributes in an electrical system are capacitance, resistance, and inductance. We model those attributes using pure and ideal elements. Pure means only has the attribute for which it is named, and ideal means linear in behavior. The variables that relate these elements are voltage, charge, current, and magnetic flux. The model structure for mechanical systems is shown here. The key attributes of a mechanical system are springiness or compliance, damping or energy dissipation, and mass or inertia. And the variables that relate these pure and ideal elements are force, displacement, velocity, and linear momentum, which is the product of mass times velocity. So the analogy between the electrical system and the mechanical system is obvious. In the application of mechatronics, mathematics is essential. Derivatives and integrals appear in the equations of motion, of dynamic physical systems and in the constitutive equations of the elements that comprise mechatronic systems. However, we will not need to actually perform integration and differentiation, as we will be operating in the domain of algebra through the use of a differential operator. However, it is essential that you understand the physical meaning of the derivative and the physical meaning of the integral. I've chosen concepts familiar to you. These are the rectilinear motion of a rigid body, such as a car, position x, a function of time, velocity v, a function of time, and acceleration a function of time. I know that velocity is the derivative of position, and acceleration is the derivative of velocity. Let's try to understand this relationship. Here you see a plot of position versus time. Here is the blue curve that shows the variation of x with time. The slope at any point along that curve at time t1 is the derivative of x with respect to time, and it's equal to the value of the velocity at that time, in this case t1. Here is a plot of velocity versus time, and we see the value of the velocity at time t1 is equal to the slope of the position versus time curve at t1. Similarly, if I look at the slope of the velocity versus time curve at some time t1, that slope will equal the value of the acceleration at that time t1. Here is my acceleration time plot. Here is the acceleration time curve. And here is the value of the acceleration at t1, which is equal to the slope of the velocity versus time curve at t1. Let's now look at the area under these curves. If I start with the acceleration time curve, and I look at the area under the curve between two times, t1 and t2, I know through integration that the area is equal to the change in velocity between those two times. In other words, the velocity at time t2 minus the velocity at time t1. That change in velocity is equal to the area under the acceleration versus time curve between t1 and t2, or the integral of the acceleration with respect to time between t1 and t2. Similarly, if I look at the area under the velocity versus time curve between times t1 and t2, that will give me the change in position, x2 minus x1, at times t2 and t1 respectively. So the integral of the velocity with respect to time between times t1 and t2 is the area under this velocity versus time curve, and that area equals the change in position at times t2 and t1, or x2 minus x1. Let's use an example from dynamics to illustrate. If I'm in a building 20 meters above the ground and I throw a ball outside the window vertically upward with an initial velocity of plus 10 meters per second, if I neglect air resistance and any kind of side wind, side airflow, the ball will travel in rectilinear motion, straight up, reach a maximum height, then straight down, where the only force is due to the force of gravity acting on the ball, and the ball has an acceleration of 9.8 meters per second squared, constant, acting straight down, as I've assumed the positive direction to be up. I'd like to describe the motion of this ball from the time of its release through its maximum height, and then when it hits the ground. This will involve integration. I will create a MATLAB Simulink diagram and let Simulink numerically integrate for me so as to describe both the position and velocity of the ball as a function of time. I start with a constant acceleration, minus 9.81 meters per second squared. In Simulink, 1 over s means integration, and I integrate acceleration to get velocity with an initial velocity of 10 meters per second. The output of this block will then be velocity versus time, which I plot. If I integrate velocity, and again 1 over s means integration, with an initial position of 20 meters, I get position versus time. Here is the position versus time plot. Here is the velocity versus time plot. And I see the position starts at 20 meters. It reaches a maximum height of 25.1 meters at a time of 1.02 seconds. It hits the ground 3.28 seconds later. If I look at the slope of the curve at various points, initially the slope at time t equals 0 is 10, and that should be equal to the value of the velocity at time t equals 0. And in fact, that's what the velocity is at time t equals 0. It's 10. At a time of 1 second, approximately, the slope is 0 horizontal, and that gives me then the value of the velocity at that time, 1.02 seconds. The velocity is essentially 0. When the ball hits the ground at time 3.28 seconds, the value of the slope of the curve at that point is minus 22.17, which is the value of the velocity at that time. If I look at the area under a portion of the velocity versus time curve, say between t equals 0 and t equal 1.02, that area is a positive 5. And that will give me the change in position of the ball between t equals 0 and t equal 1.02 seconds, which is from 20 to a height of 25.1 at 1.02 seconds. So from this simple example, we see how we will use MATLAB Simulink to perform numerical integration and likewise numerical differentiation. And we just have to understand the physical meaning of integration and differentiation as it applies to physical variables describing our dynamic physical systems. We won't need to be performing integration and differentiation. However, we will need to be very proficient in algebra and trigonometry. This concludes the presentation on Introduction to Mechatronics, Innovation, and Modeling. Thank you for your attention.